So our next speaker is Gabriela Roivainen. So welcome to Northampton Gate. Let me just give a brief introduction. Gabriela is a Doctor of Science in Electrical and Mechanical Engineering. She has got also a degree, first degree in Acoustic Engineering. She has been a lecturer at Petroleum and Gas University in Romania, research engineer at Beds of Paper in Finland. Currently, Gabriela is a senior expert at Koni Corporation. So thanks very much, and Gabriela, for being with us. And we'll be looking into your paper, into the dynamic simulations of lifts diagnosis.
Thank you. Thank you. Hello, everybody. My name is Gabriela Roivainen, and coming from Koni Corporation. Thank you for the introduction. And today I'm going to share with you the highlights of our project regarding dynamic simulations for lift health diagnosis. This presentation has been done together with my colleague, Matti, and we are going in the paper or in this presentation through several parts. We'll start with the introduction, why this work was needed. We'll continue with the targeted outputs, what we wanted to achieve. Then going to the computational strategy, how we achieve these targets, the inputs, what is needed for the work to be done, and finalize with results and conclusions. Why this work was needed? In Koni, we have a long expertise in doing simulations for many types of simulations: mechanic, acoustic, thermal, electromagnetic. And these simulations have been done mainly in development phase of our products, in R&D. However, with the faster computational solutions combined with data collected from the site, we can go beyond R&D, beyond product development, into the lifetime of the products of the lifts. The research question that we tried to answer in this paper was, can simulations provide robust data that can be used for training machine learning algorithms in identifying lift faults on the site? So we went into this cycle where we started with simulations of normal runs and malfunctions. We went into machine learning to train machine learning in recognizing the malfunctions, going there on the site in collecting data from the site to look into the data collected and see if we can identify these malfunctions on the site. By comparing simulated and measured data, we went back to the simulation in calibrated unknown parameters, for example, installation inaccuracy or damping. And then we continued the cycle until the accuracy of diagnosis was good enough. The target. So we wanted to decide which output of the simulation is suitable for this kind of analysis. And we had several constraints, and one of these constraints was that we should be able to measure this output on the site without disrupting the normal use of the elevator. And for this reason, we use in-car vibrations in 3 directions, vertical and in plan. First, because it was a suitable, it was a good output. And second, because we are collecting this data already for certain Koni elevators, so the infrastructure was there. Then for identifying the root cause of the faults, we were using fast Fourier transformation. So we were using spectrums and spectrograms of car vibration during the nominal speed of the car. So we are not interested in acceleration, deceleration. We target the nominal speed of the car, and we try to identify which frequency, which is the source for which frequency that we see in the spectrum. The next challenge was to select which components we should have in our simulation, because we didn't want to compromise neither the accuracy of the result results, neither the computational time. And as we all know, it's a difficult selection. What are we focusing on? In certain methods, like finite element, the calculation goes very deep into the geometry, real geometry. And for that reason, the computational speed is quite low. So we can spend from minutes to days to analyze a complicated structure. In other methods, like object-oriented methods or system simulation, the computational speed is higher, but the accuracy of the results is lower. And for this project, we choose a hybrid solution. We have object-oriented simulation where components are blocks with certain parameters connected through links. And for defining the parameters of these blocks, we use pre-calculated solutions where finite element method or meshless method was used. So pre-calculation for parameters and then really fast simulation in the system level. This is how the system level simulation looks like. So we have blocks, for example, the controller, ropes, guide rail, guide shoes, counterweight with certain parameters, stiffness, damping, friction, electrical parameters, and so on. However, if we have a component like machinery with a high impact on car vibrations, we divided that component into several parts, rigid part and flexible part in our paper. Which means that for the flexible part, we wanted to understand and calculate better what is the inertia tensor, stiffness, and damping tensor in 3 directions. And we use finite element solution for the bed plate, which is the part connecting the machinery to the guide rail and isolating the vibration from the machinery from the guide rail. For the car, it's again a very important component in car vibrations because we measure the vibrations on the car. And for this reason, we wanted to understand the local behavior of the car. It's a complex system. We have sling, we have doors, we have all kinds of components. And for this, we choose the meshless solution that I will explain a little bit in the following slides. So all in all, a hybrid computational strategy. Several inputs. We are discussing about the inputs specific for the components, depending on how important the components are, how important is the contribution of these components in car vibrations. We have mechanical inputs, electrical inputs. We have also logical inputs. So for example, for controller to identify the motion of the car, we use the real algorithm from our elevators embedded in a mock-up function that was running the models. About the meshless solution. So for the car, we were interested in local phenomena. So not to see just a block going up and down, we wanted to see what is happening inside the car. So we use this meshless solution, which means that if in finite element, we divide the structure into small elements and to use element-based shape function to calculate the solution. In the meshless solution, we have the shape function based on the nodes, so not on the element, which makes the structural discretization useless. So without the mesh, we can have faster analysis, faster pre-processing and faster analysis. And there is more in the paper, in the conference paper that explained the solution. For this meshless solution, we had 2 steps. In the first step, we calculated the eigenfrequencies, which are the frequencies that need very small excitation to have a huge response. And then in the second step, we rank these eigenfrequencies by sweeping an excitation with a very small increment during the frequency range of interest. So in this case, we had a vertical excitation swept with 1 Hertz between 0 and 160 Hertz. And we had a graph like this. So for hundreds of eigenfrequencies, we can focus now on 3 One that is related more to the platform. Second, that is related to the pulley beam under the platform. And third, that is a rigid body motion of the car. And we exported these three eigenfrequencies into the system level to keep the speed of the computation high. Results. We had two results in the cycle where we go from simulation to measurements and back, and to simulation from simulation to measurements in back. In the right-hand picture, we have an ideal lift, which means that no malfunctions are simulated. The curve of this frequency response for the nominal speed is blue. With red, we have the same fast Fourier transformation applied to the car vibration from a real elevator and median of 274 runs. And we can see that from 0 to 10 Hertz, we have relatively good correlation, but after that, the pictures are not, the curves are not looking the same. So we went then back to the simulation and start to model malfunctions. And we can see on the other side of the curve, on the left side of the curve, the simulated malfunctions compared to real data collected from the side. And we can identify that if we model machinery eccentricity over higher than tolerances, for example, or rope lay length due to wear, or machinery harmonics due to bad isolation of the machinery, or for example, guide shoes malfunctions like flat spot. If we model all these malfunctions separately or simultaneously, then the correlation between the measurements and simulation is better. So we can conclude that the root cause of in-car vibrations can be identified, and also that we can use them to monitor what's happening in the lift during the lifetime. Conclusions, 3 minutes. In this paper, a combination of object-oriented simulation with finite and meshless method is presented for computed car vibrations. By comparing the computed spectrum of an ideal lift with the medium measured spectrum of a real lift collected during 274 rides, we can conclude that we don't have ideal lifts on the side. So every lift has some malfunction, smaller or bigger. They are real, not simulated systems. The source of these excitations, which are different, can be identified from known frequencies or eigenfrequencies of the system, and can be simulated independently, so separately or simultaneously in the system simulation. A known variable like system damping or installation inaccuracy or other tolerances which are exceeding the prescription, the requirements, can be calibrated in the simulation based on measured data. And we can conclude that this procedure can be used for labeling malfunction of the lift and training machine learning algorithm in identifying these faults in the data collected from the site. And in the end, I'd like to thank my team and also the partners helping us to develop this simulation, SE Group and Matti. Thank you.
Thank you very much.